Long before anyone had seen inside an atom, scientists believed matter was built from tiny, indivisible units. The word atom itself meant uncuttable. Yet as experiments grew more precise in the late 19th and early 20th centuries, this idea began to crack. Atoms were not solid specks. They had structure, and that structure hinted at something deeper, something still hidden. The first clues came from studies of electricity and radiation. When scientists passed electric current through gases at low pressure, mysterious rays appeared. These cathode rays turned out to be streams of negatively charged particles, later named electrons. Suddenly, the atom had parts. It was not indivisible after all. A few years later, another breakthrough came from experiments firing alpha particles at thin sheets of gold foil. Most particles passed straight through, but some bounced sharply back. This revealed a tiny, dense, positively charged core at the center of the atom, which became known as the nucleus. Around it, electrons moved in a cloud. Matter, once thought simple, was now a miniature solar system. But a problem remained. The positive charge in the nucleus was explained by particles called protons. Each proton carried 1 unit of positive electric charge. If you counted the number of protons, you could explain the atom's charge. However, when scientists measured atomic masses, they found something puzzling. The mass of a nucleus was always greater than the total mass of its protons alone. Hydrogen, with 1 proton, was simple enough, but helium had 2 protons and a mass about 4 times that of hydrogen. Where did the extra mass come from? Something else had to be inside the nucleus, something heavy but electrically neutral, because the nuclear charge still matched only the number of protons. For years, this missing piece remained a mystery. Some scientists proposed that the nucleus contained tightly bound pairs of a proton and an electron. This idea tried to explain extra mass without introducing a new particle, but it created serious difficulties. Electrons inside the nucleus would violate known principles of quantum physics, and experiments increasingly suggested this model could not be right. The evidence pointed toward a different answer. There must be another fundamental particle, one with mass similar to the proton, but no electric charge. The search for this particle intensified in the early 1930s. Researchers were studying radiation produced when certain elements were bombarded with alpha particles. One element of particular interest was beryllium. When alpha particles struck beryllium, a highly penetrating radiation emerged. At first, scientists thought this radiation was an especially energetic form of gamma rays, which are high-energy light waves. But the behavior of this radiation did not fully match expectations. It seemed to carry more punch than gamma rays should. James Chadwick, a British physicist working at the Cavendish Laboratory, decided to investigate carefully. Chadwick was already deeply experienced in nuclear research and understood the subtleties of radiation measurements. He examined the mysterious radiation coming from beryllium when it was struck by alpha particles emitted from polonium. To test its nature, he directed the radiation toward substances rich in hydrogen, such as paraffin wax. Hydrogen nuclei, which are simply protons, are easily knocked around in collisions. If the radiation could send protons flying with significant energy, that would reveal important information about its properties. What Chadwick observed was remarkable. Protons were indeed being knocked out of the hydrogen containing material, and they flew off with surprisingly high speeds. If gamma rays had been responsible, the energy transfer would have been far less efficient. The data suggested that the radiation was not electromagnetic at all. Instead, It behaved as if it consisted of particles with mass similar to protons, but with no electric charge to cause electrical interactions. Chadwick performed careful calculations, comparing the energies involved in the collisions. The only explanation that fit was the existence of a neutral particle nearly as heavy as a proton. In 1932, Chadwick announced the discovery of the neutron. This new particle carried no electric charge, but had a mass just slightly greater than that of a proton. The missing mass in atomic nuclei was finally accounted for. Atoms heavier than hydrogen contained not only protons, but also neutrons. Together, these particles formed the nucleus. Chadwick's discovery was a turning point in physics, earning him the Nobel Prize and opening the path to modern nuclear science. Understanding what a neutron is requires looking both at its role and its nature. A neutron is a subatomic particle found in the nucleus of almost every atom. It belongs to a family of particles called baryons, which are made of three smaller constituents known as quarks. Unlike electrons, which orbit the nucleus and are governed largely by electromagnetic forces, neutrons reside deep in the nuclear core, where the dominant influence is the strong nuclear force. This force is extraordinarily powerful at very short distances, binding protons and neutrons together despite the electrical repulsion between positively charged protons. Although neutrons have no net electric charge, they are not empty or featureless. Their neutrality is the result of internal balance. Each neutron contains three quarks, one up quark and two down quarks. Up quarks carry a positive fractional charge, while down quarks carry a negative fractional charge. When combined, these charges cancel, leaving the neutron electrically neutral overall. Still, the internal arrangement of charges gives the neutron a complex structure, with magnetic properties and interactions that scientists continue to study in detail. The mass of a neutron is slightly greater than that of a proton. This small difference has important consequences. A free neutron, not bound inside a nucleus, is unstable. After about 15 minutes on average, it decays into a proton, an electron, and a tiny, nearly massless particle called an antineutrino. This process shows that neutrons and protons are closely related, two forms of matter that can transform into one another under certain conditions. Inside stable nuclei, however, neutrons can persist indefinitely, held together by the strong nuclear force. Chadwick's discovery did more than complete the picture of atomic structure. It changed how scientists thought about nuclear stability. The presence of neutrons helps explain why some nuclei hold together while others fall apart. Protons alone would repel each other strongly due to their positive charges. Neutrons add attractive nuclear forces without adding extra electrical repulsion. They act as mediators, allowing the nucleus to exist at all. The ratio of neutrons to protons becomes a key factor in determining whether an atom is stable or radioactive. The discovery also laid the groundwork for nuclear reactions. Because neutrons have no charge, they can approach and enter nuclei more easily than charged particles, which are repelled by the positive nucleus. This makes neutrons especially effective at triggering nuclear transformations. When later scientists learned how to produce and control neutron-induced reactions, they unlocked both nuclear power and nuclear weapons. These developments reshaped the modern world, for better and for worse, and all trace back to understanding the neutron. Looking back, the path to discovering the neutron shows how science progresses through puzzles. The unexplained mass of nuclei, the strange radiation from beryllium, and the careful measurements of scattered protons were all pieces of a larger story. No single observation was enough on its own, but by combining experimental skill, theoretical insight, and persistence, Chadwick was able to reveal a particle that had been hidden in plain sight inside every atom. Today, neutrons are studied not only as components of matter, but also as tools. Beams of neutrons are used to probe the structure of materials, because their lack of charge allows them to penetrate deeply without being deflected by electric fields. This helps scientists explore everything from the arrangement of atoms in a crystal to the properties of biological molecules. The once mysterious neutral particle has become a powerful instrument for understanding the world. From an invisible mass discrepancy to a cornerstone of nuclear physics, the neutron's story is a reminder that nature often conceals its simplicity behind layers of subtle evidence. What began as a missing piece in atomic weight became a fundamental element of matter's architecture. The neutron, quiet and electrically neutral, stands as one of the essential building blocks of the universe, discovered through careful reasoning, precise experiment, and the determination to explain what did not at first make sense. At first glance, electric charge seems like one of the most obvious properties in nature. Rub a balloon on your hair and it sticks to a wall. Touch a metal doorknob after walking across a carpet and you feel a spark. Lightning splits the sky, magnets cling to refrigerators, circuits power cities. Much of the visible behavior of matter is shaped by electric forces. So when we learn that one of the main particles inside every atomic nucleus carries no electric charge at all, it feels almost strange. How can something so central to matter be electrically neutral? To understand why a neutron has no charge, it helps to first think about what electric charge really means. Charge is a property that causes particles to feel the electromagnetic force. There are two kinds, positive and negative. Opposite charges attract, like charges repel. Protons carry positive charge. Electrons carry negative charge. The balance between these two determines whether an object is electrically neutral overall. An atom, for example, usually has the same number of protons and electrons, so its total charge is zero even though it contains charged parts. But neutrality can arise in two different ways. One way is through separation. Positive and negative charges exist in different places but cancel when added together. That is how atoms or everyday objects are neutral. The other way is more subtle. A particle can be neutral because its internal structure itself adds up to zero. That is the case for the neutron. It is not that the neutron lacks electric ingredients. Instead, its internal components balance so perfectly that the outside world sees no net charge. The key lies in the fact that neutrons are not elementary particles. They are made of smaller entities called quarks. Quarks come in different flavors, and each flavor carries a specific fractional electric charge. The two most common types in ordinary matter are up quarks and down quarks. An up quark carries a charge of +2, thirds of the proton's charge. A down quark carries -1, third. These fractions might sound odd, but experiments have confirmed them with high precision. A neutron is built from 3 quarks, 1 up quark and 2 down quarks. If you add their charges, the picture becomes clear. The up quark contributes +2/3. Each down quark contributes -1/3. 2 down quarks together contribute -2/3. When you add +2/3 and -2/3, the result is exactly 0. The neutron's neutrality is therefore not emptiness, but perfect cancellation. Inside, positive and negative fractional charges are constantly interacting, but from the outside, the neutron behaves as if it has no charge at all. This internal balance is held together by the strong nuclear force, carried by particles called gluons. Gluons bind quarks together so tightly that they cannot exist freely under normal conditions. The neutron is like a storm of quarks and gluons in constant motion. Charges are moving, fields are fluctuating, yet the total always sums to zero. In this sense, a neutron is a dynamic object, not a static neutral lump. Because of this structure, the neutron still has electromagnetic features, even without net charge. For example, it has a magnetic moment. This arises because moving charges create magnetism. The internal motion of quarks gives the neutron a tiny magnetic personality, allowing it to interact with magnetic fields in subtle ways. This shows again that neutral does not mean inactive. It simply means that the overall electric balance is zero. The reason nature allows such fractional charges is tied to the deeper symmetries of particle physics. Quarks belong to a framework known as the Standard Model, which describes how fundamental particles interact. Electric charge is linked to mathematical symmetries in this model. The specific values of quark charges are not random. They ensure that the equations describing electromagnetic and weak forces remain consistent and free of contradictions. In other words, the neutron's neutrality is not an accident. It is woven into the underlying design of physical law. Another way to appreciate neutron neutrality is to compare it with the proton. A proton is made of two up quarks and one down quark. Adding their charges gives +2/3 plus 2/3 minus 1/3 equals +1. That matches the proton's positive charge. Simply switching one quark type changes the total dramatically. The difference between proton and neutron is just one quark, yet that tiny internal change determines whether a particle is electrically active or neutral. This highlights how profoundly the microscopic world shapes the macroscopic one. The absence of charge has huge consequences for how neutrons move through matter. Charged particles feel electric forces from other charges and from electromagnetic fields. They are deflected, slowed, or trapped. Neutrons, lacking net charge, pass through electron clouds without being strongly pushed or pulled. They interact mainly through the strong nuclear force when they get extremely close to atomic nuclei. This ability to penetrate makes neutrons powerful probes in scientific research and key actors in nuclear reactions. Neutrality also influences how neutrons behave in electric fields. A charged particle accelerates when placed in such a field. A neutron does not, at least not in the same direct way. However, its internal charge distribution can be slightly distorted by strong fields, revealing that neutrality is not the same as uniformity. The neutron has regions where positive and negative charges are distributed unevenly on average, creating a complex internal landscape. Experiments that scatter electrons off neutrons help map this distribution, showing that neutrality hides intricate structure. The concept of charge cancellation appears elsewhere in physics, but the neutron is one of the most fundamental examples. It shows that observable properties emerge from deeper layers. Just as temperature arises from microscopic motion and color arises from specific wavelengths of light, electric neutrality can arise from the sum of smaller charged pieces. The neutron is a lesson in how the universe builds complexity through combination. There is also a deep connection between neutron neutrality and the stability of matter. If neutrons carried positive charge like protons, atomic nuclei would be far more unstable. The repulsion between positive charges grows rapidly with number. Without neutral partners to help bind the nucleus via the strong force without adding repulsion, only the lightest nuclei might exist. Chemistry, planets, and life depend on a wide variety of stable elements, and that diversity relies on neutrons being neutral. Even the processes that change one particle into another reflect this balance. In certain nuclear reactions, a neutron can transform into a proton, emitting an electron and an antineutrino. This process, called beta decay, involves the weak nuclear force. During the transformation, a down quark inside the neutron changes into an up quark, altering the charge balance from 0 to +1. The electron carries away the extra negative charge, keeping the total conserved. Charge is never lost, it is rearranged. The neutron's neutrality is thus part of a larger system where charge is a conserved quantity in all known interactions. On a cosmic scale, neutrality plays a role in the evolution of the universe. Shortly after the Big Bang, protons and neutrons formed from a hot sea of particles. Their relative numbers determined which light elements could form. The fact that neutrons are neutral allowed them to combine with protons without electromagnetic barriers, enabling the creation of helium and other nuclei in the early universe. The chemical history of the cosmos is tied to this simple property. So when we ask why neutrons carry no charge, the answer leads from simple arithmetic of quark charges to the deep symmetries of fundamental physics. It involves the strong force that binds quarks, the conservation laws that govern transformations, and the large-scale structure of matter. Neutrality is not a lack but a balance, not emptiness but equilibrium. Inside the neutron, positive and negative pieces dance in constant motion, yet the sum remains 0, allowing this particle to play its quiet, essential role in the architecture of reality. If we could somehow look inside a neutron, not with eyes, but with instruments sensitive to the smallest scales of nature, we would not see a tiny solid sphere. We would find a restless, crowded interior, a place where smaller particles flicker in and out of existence and forces of immense strength bind everything together. What appears from the outside as a single neutral particle is, on the inside, a dynamic system governed by the rules of quantum physics. For a long time, scientists thought protons and neutrons were fundamental, meaning they had no smaller parts. That view began to change in the mid-20th century when experiments using powerful particle accelerators started probing matter at higher and higher energies. When electrons were fired at protons and neutrons with enormous speeds, the way they scattered revealed that these particles had internal structure. The patterns looked similar to earlier experiments that had uncovered the atomic nucleus. This time, the evidence pointed to even smaller building blocks inside protons and neutrons. These building blocks were named quarks. The idea first sounded almost too strange to be true. Quarks had unusual properties, including fractional electric charges unlike anything seen before. But as more experimental data came in, the quark model proved remarkably successful. It could explain the observed properties of many particles, not just protons and neutrons, but a whole zoo of short-lived particles produced in high-energy collisions. A neutron is made of 3 quarks. Specifically, it contains 1 up quark and 2 down quarks. These quarks are not sitting quietly next to one another like marbles in a box. They are confined in a tiny region of space, about 1 quadrillionth of a meter across, and they move in a complex quantum dance. Their positions and momenta are described by probability waves rather than fixed paths. The neutron's mass, spin, and other properties emerge from this constantly shifting internal motion. The quarks inside a neutron are held together by the strong nuclear force, which is carried by particles called gluons. Gluons are the messengers of this force, similar in role to how photons carry the electromagnetic force. But there is a crucial difference. Photons do not carry electric charge, so they do not interact with each other directly. Gluons, on the other hand, do carry the type of charge associated with the strong force, called color charge. Because of this, gluons interact with other gluons as well as with quarks. This makes the interior of a neutron incredibly lively, full of energy exchanges and force interactions. The term color, in this context, does not refer to visible color. It is simply a label physicists use for a property of quarks related to the strong force. There are three types of color charge, often called red, green, and blue, along with their corresponding anticolors. Quarks combine in such a way that the overall color is neutral, somewhat like how combining red, green, and blue light produces white. In a neutron, the three quarks each carry a different color, and the gluons constantly swap these colors between them, ensuring the particle as a whole remains colorless. One of the most fascinating features of the strong force is confinement. Quarks cannot be pulled out of a neutron and isolated on their own under normal conditions. If you try to separate them, the force between them does not weaken as with gravity or electromagnetism. Instead, it stays strong, and eventually enough energy builds up to create new quark-antiquark pairs rather than allowing a single quark to escape. This is why quarks are always found bound inside larger particles like neutrons and protons. The mass of a neutron is another surprising aspect of its structure. The combined masses of its three quarks account for only a small fraction of the neutron's total mass. Most of the mass comes from the energy of the strong force itself. According to Einstein's relation between mass and energy, energy contributes to mass. The intense motion of quarks and the energy stored in gluon fields make the neutron far heavier than the simple sum of its parts might suggest. In this way, the neutron's mass is largely a product of dynamic energy, not just material substance. Inside the neutron, there is also a sea of virtual particles. Quantum theory allows pairs of particles and antiparticles to briefly appear and vanish. Gluons can produce quark-antiquark pairs that flicker into existence for tiny fractions of a second. These sea quarks are not permanent residents like the main three quarks, but they influence the neutron's properties. The neutron is therefore not just three quarks and some gluons, but a complex, fluctuating system. The neutron's spin, a form of intrinsic angular momentum, also arises from its internal structure. Each quark has its own spin, and gluons can carry angular momentum as well. For years, scientists thought the neutron's spin would simply be the sum of the spins of its three quarks. Experiments showed the situation is more complicated. The motion of quarks and gluons and the orbital angular momentum of these constituents all contribute. Understanding how spin emerges from this internal activity remains an active area of research. Even though the neutron has no net electric charge, its internal charged quarks are arranged in a way that gives the particle a distribution of charge within it. Measurements show that negative charge tends to be found slightly farther from the center on average than positive charge. This subtle structure affects how the neutron interacts with electromagnetic fields at very short distances. It reveals once more that neutrality does not mean simplicity. The internal structure of the neutron also explains why it can transform into a proton. In certain processes governed by the weak nuclear force, one of the down quarks inside the neutron can change into an up quark. When this happens, the quark composition shifts from 1 up and 2 downs to 2 ups and 1 down, which is exactly the structure of a proton. This tiny change at the quark level alters the particle's charge and identity. Such transformations show how deeply particle properties are tied to their internal makeup. Studying the neutron's structure requires enormous machines and delicate detectors. Particle accelerators smash particles together at high energies, and scientists analyze the debris to infer what happened inside. Scattering experiments, where electrons or other particles are directed at neutrons, provide clues about how charge and magnetism are distributed within. Theoretical tools, including complex computer simulations of quantum chromodynamics, the theory of the strong force, help interpret these results. The picture that emerges is one of constant motion and interaction. The neutron is not a static object, but a bound state of quarks and gluons in ceaseless activity. Its properties, mass, spin, magnetic behavior, and neutrality all arise from this inner life. What seems like a simple neutral particle is actually a tiny universe of forces and fields. This understanding changes how we think about matter. Solid objects, including our own bodies, are built from atoms. At the heart of those atoms are neutrons, and inside them are quarks and gluons governed by abstract quantum rules. The stability of everyday matter depends on processes happening at scales far beyond direct perception. The neutron's internal structure links the tangible world to the deepest layers of physical law. In this sense, the neutron is a bridge between the visible and the invisible. Its existence confirms that nature is layered, with each level built from more fundamental components. By uncovering what lies inside the neutron, scientists have peeled back one more layer of reality, revealing a realm where particles are excitations of fields, forces arise from symmetries, and even mass itself is largely energy in motion. At the heart of every atom, in a region so small it defies ordinary imagination, lies a dense cluster of particles packed together with astonishing intensity. This cluster, the nucleus, contains protons and neutrons pressed into a space far tinier than the atom itself. Protons, each carrying positive electric charge, naturally repel one another with powerful electromagnetic force. If this repulsion were the only influence at work, no nucleus larger than a single proton could exist. Yet nuclei do exist, and many are stable for billions of years. The reason is the quiet but essential presence of neutrons. Neutrons stabilize the nucleus not through electrical attraction, since they have no net charge, but through their participation in the strong nuclear force. This force is the most powerful of the fundamental forces at very short distances. It acts between protons and neutrons alike, binding them together when they are extremely close. Unlike electric force, which can push protons apart over relatively long ranges, the strong force operates only across distances comparable to the size of the nucleus. Within that tiny zone, it is strong enough to overcome electrical repulsion. When protons come close together, they feel two competing influences. Their positive charges push them apart, but the strong force pulls them together. Neutrons add to the attractive side of this balance. They interact strongly with protons and with other neutrons, creating additional binding without contributing extra electric repulsion. In effect, they dilute the concentration of positive charge while still strengthening the nuclear glue. The more protons in a nucleus, the more neutrons are needed to keep the balance. The idea of balance is central. A stable nucleus exists when the attractive strong interactions among its nucleons, the collective term for protons and neutrons, are sufficient to counteract the electrical repulsion and quantum mechanical tendencies that would otherwise disrupt the system. Neutrons help achieve this balance in several ways. First, they increase the number of strong force connections in the nucleus. Each neutron can interact attractively with nearby protons and neutrons. Second, because they have no charge, they do not add to the long-range repulsive forces that grow with the number of protons. This stabilizing role becomes clearer when comparing different elements and their isotopes. Hydrogen with a single proton does not need neutrons for stability. But as soon as you move to helium, which has 2 protons, neutrons become essential. The most common helium nucleus contains 2 protons and 2 neutrons. Without the neutrons, the 2 protons would not bind in a stable way. As elements grow heavier, the required ratio of neutrons to protons increases. Light nuclei are often stable with roughly equal numbers, but heavier nuclei need significantly more neutrons than protons to remain bound. The reason heavier nuclei need extra neutrons is tied to the nature of the forces involved.